Good morning. So here we go, reading computer data for a linear regression. So as we read through the paragraph there, we have a paper that's been written about because they're concerned about the drop in the number of salmon along the Columbia River up in Oregon. And so as we look at this, we have our Y value represents the maximum size of a salmonid. That's a baby salmon consumed by northern squawfish. And X is the squawfish length. Both of these are in millimeters. So they defined our variables, but again, I'm going to tell you when I write my variables, I'm writing what the content is. So to keep me in line. So we've got a set of data here. We've got an X axis, an X set of coordinates and a Y. So X is I put in L1 and Y I put in L2. And I'll zoom in just a little bit for this because some of you are complaining about that. And that's okay. So we put these in there and they want us to run a hypothesis test and answer the related questions. Well, the first thing I'm going to do is I'm going to run the least squares regression line. So I've got L1 and L2. So I'm going to go stat, calc, and I'm going to push 8. And I'm going to go second one because I have wrong numbers in there that I don't need. And I'm going to store my regression. Sorry, Elmer put it there for a minute. So vars over to y vars where I can do a function. I'm going to store it in y1, and then I'm going to calculate. Okay, so there are my numbers. Negative 89.79. My r squared is 0.96, and my r is 0.98. So I wrote those numbers in there. There's my r squared. There's my r. Here's my salmonid hat. My y hat equals negative 0.8909. I went ahead and rounded that up, plus 0.729 times the length of the squawfish. Of course, each of these are in millimeters. So I then look at where did these numbers come from? Well, to do that, we go stat, go over to test, and go to the bottom. And on the bottom there, you'll notice we have a linear regression t-test, which is what we're going to run, and a linear regression t-interval. Thank you, Mr. B, for showing me that. So here's my F. You're a good guy, Matthew. So here we're going to run a linear regression t-test. That's what this is not asking for an interval. This is asking us to run a test. So I press enter. My number's in L1 and L2. My regression is stored in Y1. In this cool, it already does it. And it said my alternative was not equal to 0. There is no difference, or there is a difference. This means there is no difference. So we go down here and we're going to calculate this linear regression inference here. And there we go. There again, there's my t-value is 15.26. My p-value is 0.000000097,156. So I just put a 0 there. You can put all that on there if you wanted to. My degrees of freedom are 9. And my standard deviation is 12.56. And so life is good. So we would reject that null because, of course, our inference value is always 0.05. And then it's got other numbers here. It also tells us our r and r squared. So then if we look, it then asks us to run a confidence interval for the true slope. So our slope, we think, is this, but using our margin of error and stuff, we're going to add and subtract from our slope to get these two numbers. To do that, we go back stat test, and then this time we're going to go a linear regression t-interval. So enter, and all the numbers are already there. And this is 0.95, a 95% confidence. We can change that if we needed to. Again, I calculate, and it gives us these two numbers, 0.62, 0.837. I made it 0.84. So we are 95% confident that the true slope of the slope of the true regression lies somewhere between 0.62 and 0.84. Simple enough. See, everything's still the same. So then what the book does, or what authors have created for us, is this data printout. This is a computer printout of that. They've run the test on the computer, and this is what it printed out. Okay, let me show you what it looked like to begin with. Hang on just a second. I've got to find that page again. Well, shoot. Voila, there we go. Sorry about that. So this is what it looked like to begin with. So we found all these numbers up here. Then we look here and say, okay, what do we see and what do we not see? Well, if you'll notice, Let me fold this over and we can do it like this. There is our initial value. It's our constant. There is our mean rate of change. This is going to be our standard error, which I have marked there. We hadn't found that yet. We could have calculated that, but there it is. There's our t-value. There's our p-value. Here's our standard deviation. Here was our r squared. Now, this one we don't need. We don't need this adjusted. Okay, nor do we need anything else along the line of constant. The only thing we need from the constant is the coefficient. This standard deviation, this t-ratio, and this p-value mean nothing to us. And then we look down here in the bottom. There's our degrees of freedom, which is the error. Everything else down here we can mark out. Let me go ahead and show you what that looks like. We got rid of the adjusted. We got rid of these numbers. We found out that was our standard error. And all of these numbers down here from analysis of variance that we don't do. And so we just mark those off. Okay, on the next part it says, excuse me, it says, what's the maximum size for salmon it's consumed by a squawfish whose length is 375 millimeters? So we take 375 and we substitute it in up here for squawfish. Multiply it times 0.729. Oh, here it is right here, sorry. 375 times this plus this, or negative that, and we get 184.3 millimeters. It then asks, what is the residual corresponding to the actual observation? They found a squawfish 375 that was eating a maximum of 165 millimeter salmonid, and so that residual is a negative 19.3 millimeters. We actual minus predicted. This was our prediction. This is the actual. We subtracted and got that number. And they said, okay, well, if you think you can do that, do you think you can do this again? So here's the output of this. They gave us the value of in thousands of dollars and number of rooms for houses in East Meadow, New York. And so they want us to write our equation. Well, again, here's our initial value. Here is our slope, our mean rate of change. There's our standard deviation. There is our t-value. There's, standard error. That's standard error. There's my standard deviation. There's my regression. There's my degrees of freedom. I mean, it gives us everything. So, and those numbers we wrote down here. And my p-value is going to be 0. And the reason why my p-value is going to be 0 is if we take our t-distribution table and we look down here, degrees of freedom was 72. Well, 72 is not on this table, but it's somewhere between 60 and 80. Well, for a 0.05 or a 95% confidence interval, we expect that number to fall somewhere between 2 and 1.99. Well, this t-value, again, what was it? 7.49. It's huge. It's huge. And I remind you, the larger the degrees of freedom, the more normal the model becomes. So if we think, wow, 72 is a high degree of freedom, and we think of this as a z-score as well as a t-score, think of a z-score of 7.5. That's 7.5 standard deviations beyond the mean. That's way to the right. The probability of that occurring is pretty much 0. Okay, interpret the slope. For every 1 increase in rooms, we expect the average increase in value to go up by $19,718. That's what this 19,718 means. Because they say it's in thousands of dollars, I went ahead and put it in terms of thousands of dollars. We expect for every 1 increase in a room, on average, the value would increase by $19,718. Okay, again, here's my R and R squared. So we interpret the coefficient of determination, the R squared. I'm going to interpret it as this. Change this back to its percent. 43.8% of the variability, 43.8% of the variability of the appraised value, sorry, I had to get my dependent value, dependent variable, 43.8% of the variability in the appraised value is accounted for in the variability in the number of rooms. 43.8% of the variability in the appraised value is accounted for in the variability in the number of rooms. Turn on closed caption and read what I said, and then you can pause it and write what I said. Okay, so we'll turn the page here. Oops, this one doesn't have the answers on it. Let's find one that does. Here we go. Sorry about that. Okay, so here's another table for us to read. So we have a change package, predict the weekly sales, number of customers. Okay, so sales hat equals my constant, $2,423. Okay, and this is in thousands of dollars. So I'm going to move this over. You could have left them as this and written in there and make sure that you say it's in thousands of dollars, but I'm going to go ahead and change them to thousands. So I move this over, and this becomes 3 zeros, 1, 2, 3, becomes 8.7 times customers, my mean rate of change. There's my standard deviation, 0.0006. There's my, that's my standard error. That's twice I've done that. Catch yourself. This is my standard deviation. This is my standard error. There's my R squared. So to find my R, I find the square root of that. Square root of 0.912 is 0.955. Degrees of freedom is 18. My p-value, is 0. They don't give us, for some odd reason, this didn't print out there, but we could pretty much come up with a t-value that would make sense for us. We have other formulas. Now, they then, on part 4, they said, all right, so 3 is the same thing as this printout. These two printouts are the same. So what's the same here? Well, there's my degree of freedom is 18. Okay, again, these numbers don't mean anything to us. There is my mean standard error. Okay, that's my standard deviation, 0.5015, they rounded. There's my R squared, 0.9119. Okay, and they made it 91, whoops, sorry, up here on the previous problem, made it 0.912. Here are my two equation parts. Here is my constant, the intercept. It calls it the intercept instead of the constant, 2.42. Here is my slope, my mean rate of change, 0.0087. Okay, there is my standard error. It says standard error for us. And there is my t-value, 13.646. Okay, so we could have used that back up on this top problem up here, but it doesn't give it to us in this problem. It didn't print out. So down here on the bottom part, here we go. Here's my intercept. Here is my slope. So it says in thousands and 100 square feet. So you could have left them as this, but I went ahead and wrote price hat equals $18,353.80 plus 387.85 square feet is my linear regression. My standard error is 0.7936. My standard deviation is 12.9965. Okay, degrees of freedom are 13. My R squared is 0.6476. Square root of that gives me 0.805. So a strong correlation here. And a p-value again of 0. And it says interpret the slope. Okay, for every 100 increase in square feet, for every 100 square feet increase, we expect the price to be increased by $387.85 on average. For every 100 square feet increase, we expect the price to go up $387.85. Or we could say for every 1 foot increase, we expect the price to go up $3.88 or $3.8785, however you want to look at it. This is if we go by 1 foot. This is if we go by 100 square feet. This is 1 square feet. Then our correlation coefficient here, we would say, no, that's correlation and determination. Correlation coefficient here, 0.805. We have a strong positive, because this is positive and this is positive, a strong positive correlation of a linear regression between the predicting the price and the square footage of a house.